the last scenario is if we have both a weak acid and a weak base. Okay, so do either of those fall under our three things that ionize? No. So it's really the simplest one, often the most missed because students try to do too much. Okay, so your weak acid and your weak base, you're simply going to carry it down. You're not going to break them apart. Okay, but you form a salt. Okay, so the only thing that's going to ionize or be broken apart is going to be your salt. Okay, because we've said that everything to this point is water soluble. Okay, so here's one of, there's hundreds, thousands of examples. Okay, so this is why all these can be different. Okay, but here we have acetic acids. You want to be sure you recognize that that's acetic acid. So very common acids and vinegar. You use that in Chem 111. Okay, so we have a weak acid and a weak base. Okay, everybody agrees with that. You look at your chart, you see it's not on your strong list, so it must be weak. All right, and then you form a salt. Okay, so if you think about the molecular equation here, if we donate a proton, this becomes NH4 plus, right? Okay. Okay. If this loses a proton, what does it become? CH3, COO minus, right? That's called acetate. So it's very common. Acetic acid, if it loses a proton, it's called acetate. Okay, so we basically already just broke it apart looking at that. Because if we combine those two charges, positive attracts negative, we form our salt, right? We have a positive and a negative charge, and that's what a salt is. Okay, so if we try to write out the ionic equation, so this is the molecular, meaning no charge. Okay, we would just simply carry down the acetic acid, right? Because it doesn't completely ionize, so we just carry it down. And then we bring down the ammonia, okay, because it's also weak. And the only thing that gets broken apart or ionized is the salt. Okay, so we write it out as ammonium, because it has a plus charge. And then we know that our acetate has a negative charge because we lost a proton. Okay, we lost a positive charge. Okay. Can we cancel anything here? You see anything that's the same on both sides? Okay, so our total ionic equation is going to be the same as our net, right? Because there's nothing that we can cancel, so this is going to be the same as your total. Okay? All right, any questions on those? There's a homework sheet that has quite a few of these on there, so I suggest doing a couple now, and this is the beginning of the unit, so you don't want to forget. That's what usually happens as we move on, and then when it's test time, you forgot about this since we start out with it. So do a couple now, and then maybe next week do a couple so that you don't forget. Yes? Because it's not strong, so it has to be a strong acid. Yeah. Yeah, so if you look at if it's strong, yes. If you look at your list and it's not on there, that means it's weak. Yeah. Sorry, I keep grabbing yours. Mine are over here in this bunch of mess. All right, any questions on that? 'Cause we're about to move away from it. Okay. All right, before we start this, really, I'm going to go ahead and pull it up here. Whoops. Okay. So our first theory that we talked about was Arrhenius. And it was our simplest definition. It said that an acid has to have a proton, it has to be an aqueous solution, our base has to be hydroxide and has to produce hydroxide in aqueous solution. Okay, Bronsted-Lowry, okay, it encompassed a few more of our acids and bases. Okay, so you still see this theory some today, but it said that an acid is a proton donor and a base is a proton acceptor. Okay, it does not have to be in aqueous solution, meaning in water, okay, or produce hydroxide. Okay. The last theory is our Lewis theory. Okay, this is the best theory. This is what is the present day theory, and it is the top of the umbrella, or however you want to think of it. It encompasses all acids and bases. So if I ask you, is HCl or any acid a Lewis acid, the answer is yes, because it includes everything. Okay, so I could name every acid and thousands of them, they all are Lewis. Okay, so that's why it's the best theory, because it brings in everything. So it's all your acids and your bases. The other reason it's so important is it takes your Lewis structures. So I know we're going to draw one here in a minute. Okay, it takes your Lewis structures, which represents electrons. Okay, so you may or may not remember, hopefully you remember Lewis structures, at least, drawing them at some point. Okay, but your Lewis structure is a representation of the valence electrons in that molecule, meaning the outermost reactive electrons. Okay, and so when you draw a Lewis structure and you represent the electrons, okay, our Lewis theory talks about how these electrons get transferred, how they move in a chemical reaction. Okay, so I'm biased, I'm an organic chemist, but not just organic chemists. Every chemist is going to look at a reaction and look at the electrons, because that's what's being moved around, involved in a chemical reaction. That's really all. Protons, that's fine, but electrons is what's causing the reaction to occur, and looking at the details of it, that's what a chemical reaction is. That's what's going on at the molecular level. Okay, so our Lewis theory says it's going to base everything on electrons, not on protons. Okay, so it's going to look at an acid is an electron pair acceptor. Okay, so let's write this out. Okay, we're going to show this here in a second. Okay, so a Lewis acid, I'm just going to say La, is an electron acceptor. Okay, and a base, a Lewis base, is an electron donor. Okay, so if our Lewis base is an electron donor, it's got to have some electrons, right, to donate. Okay, so normally your Lewis bases here, okay, they may have, lone pairs. Okay, that's a good indicator of a Lewis base, because it has those extra pair of electrons. Okay, that's what makes it a good base. And there's other indications as well, but I don't want to confuse you right now. Start simple. Okay. Actually, before we even start this, if you had me for Chem 111, or I may have even mentioned it here, one of the things I stress, and one of my favorite term, as I say, is electronegativity. Okay, so that's one of the words that I use a lot. Okay, and we don't get to use it quite as much in Chem 112. Okay, does anybody remember what that means? Anybody? You had me? You don't have to give me the exact definition. Just what does it mean to you? Do you know which atom's the most electronegative? Okay, so you know something. So fluorine is most electronegative. Okay. Okay, very good. So the further we move, okay. Okay, but what is it doing? What does electronegativity mean? If it's the most electronegative, okay. Okay, so let's say we have this bond right here, HF. Okay, and you just told me that fluorine's the most electronegative. What is it doing with respect to the electrons that are in this bond right here? Say it out loud, Sergio. It attracts them, exactly. Okay, so that's what electronegativity is. It's an attraction electrons to itself. Okay, so in my class, I bring out this little, I should have brought it today, but it's actually a rattle. But anyways, it's got a rope on it, and we talk about it being like a tug of war, okay, between this atom. Let's say if this was the rope, okay, here we have, 2 electrons in every bond, right? Okay, and if you have a tug of war between hydrogen and fluorine, who's going to win? Fluorine, yeah, by a landslide. So if you draw, usually you see this, you'll see an arrow kind of pointing towards that means the electrons in that bond are shifted closer to the fluorine. Okay? So how we denote this is we say that the fluorine's partially negative. That little squiggly thing is a partial sign. And the hydrogen is partially positive. Okay? So if it attracts electrons, electrons are negatively charged, right? So it makes sense. If it pulls those closer to itself, it's going to make it have more of a partial negative charge. Okay? Something else I wanted to say. Okay, the second thing, this is how I start my organic class when we, very first day of class. We talk about this. And then I talk about the idea behind a chemical reaction is this. This is the driving force behind any reaction. Okay, if you don't have somewhat of a reason for two molecules to react, they're not going to, say. So if you don't have this kind of shift in electronegativity, okay, if it is reacted with, something else here, so let's put water, okay. If we were to draw the Lewis structure of water, it looks like this. We have a partial negative on oxygen, right? Because oxygen is more electronegative than hydrogen. Okay. These two will react. HF will react in water. We saw that even when we used the Bronsted theory. Okay. But the driving force behind this is the fact that we have reactive sites, meaning we have this unequal distribution of electrons. Okay, so just like a magnet, if you hold the positive and the negative end together, what are they going to do? They're going to attract. Exactly. And that's the same idea here. Okay, so if you look at this in this molecule, okay, what do you think this fluorine is going to be attracted to in this water molecule? The hydrogen. Does everybody agree with that? Okay, and that's what we're going to see. We're going to see that we're going to donate electrons, so positive and negative attract, and they form a bond. If you have no unequal distribution of charge and no reason for something to react, it's not going to react. So it all comes down to electronegativity and acid-base chemistry, which is what we're doing, okay, and the fact that unlike charges attract. Positive and negative attract. Okay, so here's an example. Okay. In the Lewis theory, it's important that you can draw a Lewis structure. Lewis, same guy, in the Lewis theory and the Lewis structures. Okay, so here it is drawn out. Okay, we're going to go through and draw the structure of ammonia just as a refresher. I posted some videos online of just random ones I've made that can help you, or go back to your old notes or whatever if you've forgotten how to draw a Lewis structure. Really wish I had more board space here. Say that every day. Okay, so if we have NH3, okay, if you had, how many of you used the NASB method? Do you remember? Or if you had me, you used it. Okay. All right, the NASB method is what we're going to do today. Okay. The N stands for needed. So how many electrons do each of these atoms need? Okay, the key here is that all atoms besides hydrogen need 8. Okay, so nitrogen needs 8. Hydrogen, see it's up there, it only needs 1 electron, right, to be like the nearest noble gas, so it's only ever going to have 2, right? So you just add these together, so you have 3 hydrogens, so you're going to have 2 plus 2 plus 2, or you can do 2 times 3, whatever, doesn't matter. You just add them together. Okay? So that gives us 14. Right? Available, this is the same thing as valence. Okay. Anybody remember how you can look at the periodic table and determine valence electrons? The group number? Okay. So what group is nitrogen in? 5. 5. Okay. And what group is hydrogen in? 1. It's our only non-metal that's over there with the metals. It's kind of confusing. Sometimes you see it over here, but it is in group 1. Okay, so we have 1 plus 1 plus 1. So we have 8. Okay, so for our needed, everything needs 8 besides hydrogen, and then the available is the valence. Okay, and to get S, which is shared electrons, you take 14 minus 8, which is 6. Okay? So that means that you're going to have 6 electrons shared in bonds, right? So S and B pretty much go together, but in every bond, how many electrons are there? 2. So if you have 6 shared, that means you're going to have 3 bonds, right? So if you divide by 2, you get 3 bonds. Okay, so we draw nitrogen. So we try to draw kind of our framework, okay, because we have to use the atoms that were given. Okay, we know nitrogen goes in the middle because hydrogen never does, right? It only wants to make 1 bond. It can't be the central atom. All right, so if we drew it out just like so, and we have all of our atoms accounted for, and we have 3 bonds, right? Which means we have 6 shared. So this looks good, easy enough. All right, but we have to come back, and this, okay, the point of our Lewis structure is that this matches up with what we draw. Okay, so how many electrons do I have drawn there? 6. How many do I need? 8. So I'm missing 2 electrons. Okay, hydrogen never, ever, ever has lone pairs on it, right? Because if I had a lone pair, then I have 4 electrons around hydrogen, which it will never have that. So if I can't put electrons around the exterior, I go to my central atom, and this now has a lone pair. That lone pair is super important. If you don't draw it, then you didn't draw a base. Okay, that lone pair is what makes this nitrogen or this ammonia basic or a weak base. Okay. All right, so there's its electron. So if we were to draw our charges here, okay, we would draw a partial negative on nitrogen and a partial positive there, right? Okay, we know that makes sense. We've also got a lone pair there. Okay, if it reacts with water, our Lewis theory says that the base donates an electron pair. Okay, so this is what we call a mechanism. This is a simple mechanism. Okay, a mechanism means that we're showing what's happening with respect to electrons by showing the arrows. Okay, you're going to start at your base with your arrow. Okay, the tail of your arrow is going to attack the acid, okay, wherever it is positively charged, right? Okay, so if we had, I really wish I brought my iPad here. Okay, so we have this. Okay, we have water, which we know is going to be our acid. Yes. Okay. So Lewis theory says our base is going to donate electrons. So we're going to start where we have electrons at our base. And we're going to show these electrons being moved and donated to our acid. Okay? Am I going to draw my arrow to the oxygen? Or am I going to draw my arrow to the hydrogen? Okay, it doesn't matter which one. Of course, we could flip it around, but it doesn't matter. Okay, so we're going to draw an arrow like this. Okay, when you make an arrow from the tail to the tip, you just formed a bond. Okay, so you move those electrons to make a bond with hydrogen. Okay, so if we left it like that, how many bonds are around hydrogen? Okay, it's got 2 bonds, meaning 4 electrons. Okay, is hydrogen going to want to stay like that? Absolutely not. So these electrons here that bond is going to break. Okay? And the electrons in this bond are going to be essentially dumped onto an oxygen. Okay? So we show that here. There's our bond. When we form a bond here, we take a neutral ammonia and form ammonium. Okay? Because we lost electrons, right? Ammonia donated its electrons, so it's going to go from neutral to being positive. Okay? And then here, we broke this bond and put more electrons on the oxygen, so it's going to be negative, right? Where? This is hydroxide. Yeah, just OH minus. Yep, exactly. Okay. Okay. This right here means you just formed a bond. So if you want to think about it, this is that. You see that?
So did it kind of yank it away?
What? The ammonia?
Did it yank the hydrogen away?
It donated electrons to it to form a bond. It formed a bond with it.
It broke away from.
And then these electrons, because there's too many electrons on hydrogen, that bond breaks and dumps electrons onto the oxygen.
Hydrogen remains with the bond.
Yes, when it makes a bond, the tip of an arrow to the tail or the tail to the tip, if you make a bond, they're bonded together.
And that's how you did it before.
Exactly, because you made a new bond, which is what chemists want to do. We want to form bonds, okay? And hopefully as efficiently as we can. Okay, we're going to do an exercise and see if this
You said
helps.
it one way, but I know what you're thinking. When it made the
You get
bond,
it?
one is the product, one is the reactant side.
Yeah, this is the products. Yep. Okay, so our reactants react
I thought it was
to form a new bond. Okay, and you could still look at this as Lewis theory too. I mean, not Lewis, but Bronsted. It still donates a proton and accepts a proton. So you still get the same answer. It's just looking at the electrons. Okay? So if you think about it as your acid donates a proton and your base accepts, it's still the same thing. Okay, as the Bronsted-Lowry, we're just showing it with respect to electrons and how they move. Yes? Because you made a new bond. Okay? So you start over here. Okay? A bond is made up of electrons, right? Okay? If those electrons are donated here, it forms a bond. This right here means you formed a bond. Okay? So I wish of all days I don't have my iPad here. Okay, so if I draw the products here, okay, this means I made a bond, okay, from here to here. So when I make a bond, so we'll make this, let's call that my new bond, because I donated electrons from here to here. I made a bond between the nitrogen and the hydrogen. So there's my new bond. Make sense? Yeah, that's the point. You create a covalent bond. Means a sharing of electrons between two atoms. Exactly. Yeah, we wouldn't have the same thing on both sides, right? Yeah. Okay, and then in this example, we have too many electrons around hydrogen when we make a bond. So if we can't leave it like this. Okay? Does everybody see that? So here's our new bond. Okay. Oh, let me put it up here. Okay. What's wrong with that if we didn't do this second part? Hydrogen has how many electrons around it? 4. So that bond, okay, from the tail of the arrow to the tip means we moved electrons. There's 2 electrons in here, so they get moved onto the oxygen. Okay, and that's where we get hydroxide. Okay, I need 5 volunteers. We're going to try to show this. It's my first time to try to do this. It may be a catastrophe, but we're going to try. Okay, anybody? All right, Damien, Aaron. Okay, we'll get you guys set up first. Okay, y'all don't have to stand real close together. Okay, let me turn you, let me see. Okay, all right, you're going to move down this way just a little bit. Okay, you're going to hold this. Okay, and you're going to get real close. Y'all are bonded together. Okay, got it? Okay, I need 3 more volunteers. Come on. Thank you. All right. You're going to be in the middle. Okay, come on this side. Okay, you get on this side. Okay, y'all got to get close together. Y'all are bonded together too. Okay. All right, I'm going to get I can use a marker, I believe. All right, so what we have here, I really don't have these space now. So I have HCl. Everybody see that? Right here, they're just backwards. It doesn't matter because we're going to be attacking this guy there. Okay. And what else do I have? I have water, right? Okay. So we're going to go ahead and draw out that Lewis structure. Okay. All right. So if we look at each of these, okay, who's the acid and who's the base? Acid over here. Okay. Our definition of an acid for our Lewis theory is that it is an electron acceptor, right? Okay, so the first thing we want to do is look at this bond. Okay, who's more electronegative? Well, you even match the color of your shirt. Okay, so we're going to put a partial negative there. That does not look like partial, but okay, looks like an 8. Okay, what about this hydrogen? Partial positive, which makes sense, right? Our proton becomes H+. Okay, so partial positive. Okay, all right, over here, so this is our acid. Okay, these guys are my base. Okay, if we look at this, what's our partial negative charge going to be on? The oxygen, right? It's got those lone pairs too, okay? So we're going to make it partial negative. Okay. Everybody good with that? And I'm covering it up here. All right. If we think about what happens with our charges, okay, so what you want to remember here is in each of these bonds we have electrons, right? Okay. So okay. These are covalent bonds because we're sharing electrons in those bonds. Okay. All right. Our definition says that a base is what? It donates what? Electrons, right? Okay. So we start here at the base. Okay. So if we look here, where are electrons that are going to be donated? On the oxygen, okay? All right, so you guys, okay, are going to come like this, and you may have to reorient yourself in a second. Okay, but this right here, okay, has to attack what? This, okay, because opposite charges attract. All right, so I want y'all to move over here. So if they were floating molecules in a solution, they're going to come over here. They're attracted to Damien. Okay. All right, we're going to get too close together here. Okay, and now I want you to form this bond. Okay, so you're going to have to hold over here. Okay, but notice that hydrogens stay attached, right? We didn't lose these guys. They're still bonded. The whole molecule, came over to the acid. Y'all getting in y'all's bubble a little too much, sorry. Okay, so okay, so we make a bond, right? Okay, there's our bond. Okay, these guys are staying attached. Okay, so now if we look, this is our new bond that we just created. Hey, everybody's kind of here together. Okay, but the hydrogen is not happy, is it? What's wrong with it? Okay, so poor little Erin is going to get kicked out, right? And she comes over here all by herself, but she is kind of happy because now she's got a lot of electrons, so she's negative. Okay, this is our new compound. We formed a new bond, right? Because the electrons from this oxygen were donated to Damien's hydrogen. Okay, so here's our new bond. Okay, we have 2, 4, 6 shared electrons. Okay, and then because we donated 2 electrons, we don't have those 2 anymore, right? Because they made this bond. Okay, so all in all, we made hydronium, which has a plus charge, right? Because oxygen now here is making 3 bonds. It lost electrons because it donated them here, and so we made H3O plus. Okay. Thank you, guys.
Thank you.
Good job. Yep. Okay. So we had HCl. This one's HBr. So same idea. Okay. Electrons move in, and a lot of times electrons then move out. Okay. You see that a lot, not all the time. Okay. But if we move in and we form a bond and we have to break one, then we do a move in, and electrons have to move out. Okay. Okay. So let's take water. Okay, so let's take our autoionization of water. So it doesn't really matter. We've got 2 water molecules. One can be the acid, one can be the base. Okay, and let's draw the Lewis structure of water. And then let's try to draw the mechanism. Okay, so here's water. Has 2 lone pairs if you go through the NASB method. Okay. This one's going to be my acid, and this one's going to be my base. So I'm going to turn it towards it like that. Okay. The reason that that water can act as an acid or a base is because it has both components in it. Look at it. It's got an electronegative oxygen that could act as a base. But then it has a proton on it that can act as an acid. So it's got both. It's kind of why it's called amphiprotic and why it autoionizes. Okay, so this is my acid. Partial negative, partial positive. So I'll put all my charges here. Okay. This one's my base, so this is where I'm going to go to my negative charge. Okay, so if I draw my mechanism here, it looks funny there. This is partial. Okay. All right. I start at the base where I have my electrons to be donated, and then they attack a partial positive charge. Okay, so I'm going to go like that. Okay, so when I draw that arrow, what did I just form? A bond. So now I have H3O plus, right, when I'm on the other side. Okay, same scenario. Hydrogen can't have more than one bond, so that breaks, and electrons move to the oxygen. Okay, so we form a bond here. So we already had this. Make my new bond a different color. Okay. And there's my new bond. So we'll make this red. You have 1 instead of 2. If you want to draw the Lewis structure, you don't have to draw it there. But okay. And then, so we have our, okay. Then this is like this OH here is like how Aaron was our chlorine. Okay. It gets kicked off, but these are still bonded, right? So it's just going to kick it off and give you that. So you're going to have, if you want to draw in all the lone pairs, you can. If you have, well, really you could use it there if you wanted to, but it's just habit. I know the oxygen is what's positively charged, so I just draw it on the atom. But you could put it in brackets and then put it positive if you wanted to, yeah.
So the brackets are so that you can put the charge outside of it?
Yep.
Is that the only purpose they say?
Yep. Well, for Lewis, yeah, for these. We use brackets in other ways too, but
It just serves to put the charge out.
yep.
That was confusing about 1 and 1.
Okay, so here's the kicker here that can be a little confusing. All right. So if we look at our example, or think back to our example. All right, let me go back just a second. Okay, look at this. If we were to label this as Arrhenius or Bronsted or Lewis or a combination, we know that's always Lewis, right? Okay. Could we still call this a Bronsted reaction? Yes. Okay. So if we could still, all the examples that we've used, still could fall under Bronsted, so then why in the heck is Lewis even a part of this? What makes it different? Why does it encompass more acids and bases than your Bronsted? Okay. So the answer to that is in this slide here. Okay. In the Lewis theory, okay, I just showed you how to transfer electrons and all that. Okay. Okay, here's an example of what I'm about to say. But your acid doesn't have to have a proton at all, okay, in this theory. Okay. What it says, and this is what's this red here, acids have a positively polarized hydrogen, which is what we've been seeing, right? That's been common throughout all this, or an empty p orbital. Okay, so I know that really throws you back into Chem 111, so we're going to look at this, okay? Meaning that it can accept electrons. If its orbital is empty, then it wants something to be donated to it, okay? So not only do Lewis acids and bases encompass all the acids and bases of Bronsted and whatever, okay, they also have some kind of special, some of them are metals, some of them are not, but compounds that are called Lewis acids. Okay, so the main difference is in the acid. Okay, so the ones that I want you to know, I'm going to put up here. Okay, that way you don't have to, you can, okay. Okay, BF3 is the example we're about to look at. Okay, boron is one of our elements that doesn't have to, or it kind of defies the octet rule. Okay, the octet rule is that your atom wants to have 8 electrons around it in its structure. It defies that. It's happy with 6. Okay, so if it's happy with 6, then that's what makes it a good Lewis acid, because you can donate electrons to it. Okay, another one is titanium, tetrachloride. We call it Tickle 4. Okay, and then aluminum chloride. So there's a lot more than these, bless you. Okay, but these are the 3 most common that I want you to know. Okay. Do what? Boron trifluoride. Sometimes it's called boron fluorate, but boron trifluoride. So these are Lewis acids. Okay. Or aluminum chloride. Okay, so why are these Lewis and not Bronsted? Bronsted-Lowry says an acid has to be a proton donor. Okay, so why are these not under Bronsted? they don't have a proton, right? And they are actually extremely good acids. And these are used a whole lot for all kinds of different reasons. Okay, so to know how or see why these are Lewis acids, we draw the Lewis structure and look at the picture. Okay, we look at the big picture of why this is the case. Okay, so if we have a base, so we're just going to say fluorine here, it's got that negative charge. Okay, anytime you have negative charge, that means it has electrons, right? Okay, so it's going to donate. Okay, notice we have our mechanism here. Okay, our base is where we start. It donates electrons to an acid, but this time we don't have a proton. Okay, but it donates to the boron. Okay, the reason for that, okay, you look around boron, how many electrons does it have? 6. Okay, we know most elements want to have 8. Okay, so if we look at this, you may not remember orbitals that well. Okay, but basically you have this this empty p orbital. Okay. It's okay, BF3 is not going to decompose, it's happy like that, but it's also fine with 2 more electrons being donated to it. Okay, and so that's what makes it an acid, okay, because it's an electron acceptor. Okay, so when we donate that fluoride, we make a new bond, right? Okay, so we make a new bond, okay, and we filled our empty p orbital. Oops. Okay, this time nothing breaks off. So we don't have a hydrogen that has too many electrons, because boron is stable like this as well, because it has 8 electrons around it, which is fine, right? That's our octet rule. Okay. It made this. It made a coordinate covalent bond, a boron-fluorine bond. It no longer is BF3, it's BF4. Okay? So it gained a fluorine bond. Okay? And it has a negative charge because it went from being neutral to gaining electrons. So that's what gives it the negative charge. Okay, so look at this. This kind of just brings back all. You'll have a couple problems like this on your exam. Okay, look at this reaction. Okay, and I want you to tell me, is this a reaction, an example of an Arrhenius, a Bronsted, a Lewis, which we know is always Lewis, or a combination? Okay. It's going to be a combination. Yep. Combination of which ones? Okay, somebody said Lewis and Bronsted. Anybody else? Everybody agree with that? Okay, why is it not Arrhenius? It's not in water first, right? And our base is not hydroxide, right? Our base is ammonia. So exactly. So this will be an example of a Lewis and a Bronsted. The previous reaction that we looked at, this one right here, this one would only fall under Lewis, right? Because there's no proton on an acid, right? All right, so very good. All right, any questions on this? Okay. All right, one thing to think about, I just threw this in here, a little synthesis question. Okay, you can read it. I'll give you a second to read it and think about it. Think about what's in your stomach. Yeah, 1 molar HCl is in your stomach. Mm-hmm.
Well, the weak acid will not really ionize in the salt water.
Very good. Yeah, that's a very, okay, a weak acid is not going to completely dissolve or ionize, right? And if you want the medication to be, effective, you want it to dissolve. Okay, whereas, salt, we've said if it's water soluble, completely ionizes. Okay, so if we this is kind of just a general abbreviation for a weak acid, is just to write out HA, so whatever the acid is. So this is a weak acid. Okay, so if we're going to convert it into a sodium salt, then we need to use a base that has sodium in it, right? So we could say, NaOH is fine here. Okay. Okay. So our salt, so we'll form water. Okay. And then we're going to form Na, and then whatever this is. So we have our positive, and then this acid's going to become our conjugate base. So we can write that like that or that. Okay. So if we have a positive and negative charge, this would be our salt. So this is what chemists do. They'll take a weakly acidic drug, and then they react it with a base to make it a sodium salt. Okay. And like Tina said, this salt will completely ionize. Okay. But also, if you think about, if you have a weak acid, its conjugate base is going to be what? Strong, right? So this A minus is going to be strong. Okay, you can also think about this, the taste of medications as well. Okay, so usually an acid or a base is going to taste pretty gross. If you convert it to its salt, it's going to taste a little bit better. I mean, enough to most, are pills you swallow, but you'll be able to handle the taste a little bit better. So it also helps with that. Okay? That's a big deal, especially for kids' medications and things. So, okay, so if it's stronger, we convert it to a salt, which is strong. It also completely ionizes. So that means when a strong, here's our conjugate base or conjugate salt here, reacts with HCl in our stomach, it's going to react instantaneously and completely. So it's going to completely react and ionize, and you're going to get the active component of the medication, okay, and it's going to be soluble in that form. All right, let's see what time it is here. We're not going to get much into this. So this is actually stuff you already know. So just a review. Okay. So chapter 10 and 18, they're out of order, but they seem to kind of go together pretty good. So I have those in that order. Okay. The three things that we've said that will completely ionize are strong acids, bases, and water-soluble salts, right? Okay, so if they completely ionize, meaning that when you put them in solution, you form all ions, so no molecular compounds, okay, then are those weak or strong electrolytes? Remember? Okay. They form ions. Are they going to conduct an electric current? Yes, exactly. Okay, so those two go hand in hand. If they will form ions, these three here, then they're going to be good conductors of electricity. And this goes back to, you may not remember, but the lab, I told you had the electrode and you went through. And so one of the, I think it was the NaOH was the highest, registered the highest amount of ions. Okay, that means it's the best electrolyte. Okay, so the more it dissociates, the more ions, the more electrical current that can be produced. So if any of you are going into electrical engineering, a lot of this, and you go, of course, more and more detail, but is, kind of a factor behind all of that. So, okay, so we have to distinguish weak acids from strong, which we've already done. Okay, an electrolyte is a compound that will ionize or dissociate into its ions in aqueous solution to produce an electric current. Okay, and so we've already established what those three are. I have them here anyways, just to remind you. Okay, our strong, so I'm starting here at the bottom. Electrolytes, they approach nearly 100% dissociation, meaning they form ions. So we went through and we wrote out net ionic equations for those things that will completely ionize. We broke them apart, and we pulled out their ions, okay, because that's what's actually being produced in solution. If you have a weak acid or base, okay, these dissociate much, much less than 100%. Okay, some are even less than 10%, okay, meaning you're going to get 90% of unionized molecules versus maybe 10% of ions. Okay. Here's our first class. It's just an example. We have a strong acid. It completely ionizes in water. We've seen this. We've shown it with the Bronsted theory and with our Lewis theory. And we have this arrow, this single arrow, which means 100%. Okay, there's 100% conversion. So after this reacts, there's none of this anymore. It's all ions. Okay. Strong base, same idea. Here's two strong bases. We have the single reaction arrow, meaning there's no equilibrium, no going back and forth. We produce all ions here as well. And so both of those bases should be on your strong base list. And then water-soluble salts. To us at this point, all are water-soluble until we get to chapter 20. So here's some salts, metal, non-metal, combined together, okay, and then they break apart into their ions. So we would get 100% of, so if we placed calcium nitrate in water, we're going to get 100% of this, of ions. Okay. Non-electrolytes, these are molecules that exist as our molecular molecules and not as ions. Okay, so they're just going to stay, they're not going to break apart into ions, they're just going to stay as they're, like ammonia. Okay, it's going to stay as NH3. It's not going to break apart or ionize. Okay, so weak acids and bases do this, so they're not going to dissociate.
Did you say ammonia?
Mm-hmm.
Okay, so I always think ammonia is you need to dilute it with water. Break it apart.
Yeah. Okay, ammonia. So it's this. Okay. If you place it in water, okay, you're going to get an equilibrium. Okay. You're going to get some oops. Oops, hang on. Oh, that's right. Okay. You're going to get some ions, okay, in water, but it's weak. So most of it is going to be this ammonia molecular. Okay. But you do produce some. So some of you asked me, even in lab, we had, I told you to use a certain molarity ammonia, and you came up and asked me, this isn't ammonia, okay? But it was, right? Because when it's in water, it produces ammonium hydroxide. Okay, so you have some of this, but it's still a weak base because you have mainly this unionized, but you have some, not a lot, of this, of your ions. Okay. Okay, we've seen that water reacts with itself, right? So we produce hydronium and hydroxide. Okay, so if we think about, we have an equilibrium arrow here, right? Okay, because this is our autoionization, so go forward and reverse. Okay, when we have equilibrium, think back to chapter 17, when you came up with Kc, right? It was concentration of products over reactants, right? Okay, well here both of our reactants are water, and we consider them to be what's called an activity, meaning they're one. So they kind of just cancel each other out. So our Kc in this situation is just the concentration of the products. Okay, you can think of it as over 1 if you wanted to. Okay, so instead of just calling this Kc, because that's what we were using in chapter 17, we're looking at water So we call it KW, W for water. So this is what you'll see it written as. Whoops, I got ahead of myself here. We have to go back as this. Okay, so KW equals the hydronium concentration times hydroxide. Okay, so when you experimentally test this out and you take pure water and you find the concentration, okay, at room temp though, this changes if you change temperature, but at room temperature, if you determine the concentration of the hydronium and the hydroxide, it is exactly equal, okay? And each of them has a concentration of 1.0 times 10 to the negative 7 for hydronium and the same for hydroxide. So if you multiply those together, you get this. So KW, that's an equation that we're going to be using. KW, I know it's still KC there, but KW, oops, equals hydronium concentration times hydroxide concentration equals 1.0 times 10 to the negative 14. So you'll have to know this. You'll have to know that value as well. Okay, and that's because this is the basis of our pH scale. So if both hydronium, what do we think of when we think of H3O plus or H plus? We think of an acid or a base? Acid or base? Acid, right? That's what an acid is. It's hydronium or H plus. Okay, and we think of hydroxide, what do we think of? Base. So if both of those concentrations are equal, then what do you think the solution is? Is it going to be acidic, basic, or neutral? Neutral, exactly. So that's why we can base our pH scale off of water, because it just uniquely, over any other reactants, or especially one single, it's just water. There's not anything else in there. Okay. The ions, when it produces, and we have its reaction equation, which we showed, we always have the same concentration of both. Okay. Does anybody know what the pH is when something's neutral? 7, yeah. So what about if it's 0 to 6.9? Is it acidic or basic? Acidic, yeah. Below 7 is acidic, and above 7 is basic. Exactly. Okay, so if we look at, this is what we already showed. This is KW. Okay, and that's what you've got to know, that equation. Okay, so if we have a different solution, last thing, guys, I promise. I know y'all are getting ready, antsy to go. Okay, if you have more hydronium in a solution, so now we don't have water, we have another solution. If we have more hydronium concentration, it's going to be an acidic solution, right? Okay, it's not neutral anymore. They're not equal like water. Okay, if they're equal, okay, which you can do some tweaking and try to get solutions to be equal. That's what you do when you titrate. You add the acid and base exactly the same amounts to get neutral. Okay, if you have more hydroxide in your solution, then it's going to be basic, right? And that's what determines whether something is acidic or basic.
When we're talking about water in these situations, are we talking about distilled water?
Yes.
Not tap water?
Yes.
Because tap water can be
It just depends on how pure it is, if it's contaminated or not. So yeah, and
trust it. We wouldn't use
and the drinking water around here, you're going to have calcium, magnesium, fluoride, nitrates, from all the limestone and everything. Carbonate. The carbonate can make it more basic. So yeah. All right, for those of you that want to look at your exams, ask questions, I'll see you all at 1 o'clock. Otherwise, I'll see you on Thursday. Yeah, hey, wait, don't leave. I got your exams. Don't leave. Almost forgot again. I'll have to look. I don't think so. I don't think. I think it's the week after that. Okay, come up and get them. Alex, Damien, Sion.
It's October 30th.
Yep.
Is that next week?
Wow, it is.
No, it is, isn't it?
There you go. We're going too slow. We're not going to be there in time. Jennifer, we may have to. I'll look at it. I'll send out an announcement if we. Martin, Michael, Sam, Tina, Sam, Hunter. Reed, Cole. Somebody, where's Michael at? Oh, you're over here. Excuse me. Jeremy, Michael, Civil, Aaron, Richard's not here, Katie, Justice, Brad, Brian's not here, okay, Philip, Sergio, excuse me. All right. I don't know. I'll look at it. I've got class right now, but we'll probably still have it. Just we may not get to everything that we normally do. Somehow we've gone slow, I guess.